Hi there, my name is Wolfgang and I'm a teacher and saxophone player and work at the Akureyri Vocational High School in northeastern Iceland. Now in the first week of this course we've learned about different properties of sound. Today one of the components of sound I would like to talk about, and that's the frequency. Sound originates from a vibrating source and the vibrations are transmitted via a medium, in music most commonly air, and get to the ear of the listener. And there they are transformed by the brain and recognized as a certain sound. For example, in a guitar, it's the guitar strings that vibrate. In a trumpet, it's the trumpet player's lips, or in the saxophone, it's the saxophone reed. The human ear perceives frequency as pitch. Our ears are quite good at distinguishing pitch at certain frequencies, but to measure pitch or frequency exactly, we would have to use a measuring device like an oscilloscope or a spectrum analyzer. So if I played, for example, on my saxophone the note middle A, there would be a wave occurring in an oscilloscope and it would show up like this. This would be the middle A. Actually, any given note on any instrument doesn't consist of one single frequency like I show here. This is just a simplification, or is actually showing a sine wave, but sine waves don't occur in natural sound sources. So the saxophone middle A would be composed of various frequencies superimposing on each other, but still you can think of the above waveform as an average of the waves that are actually occurring. Now if I were to play the note A one octave higher, the frequency would simply double. So we would get this kind of picture on an oscilloscope. And we have the A signifying amplitude, and we have the T here for time. So there is no increase in amplitude as related to the first A I play. You see that only the frequency has increased. Frequency is most commonly measured in hertz, which is the number of wave tops per second. So you would measure over a certain amount of time, say 1 second, we have this number of wave tops, and that's the frequency in hertz. Now if I played a low A, then the frequency would only be half the amount of the middle A I played first. So if I have a low A, you would see this kind of wave. To enable a saxophonist to be able to play in tune with other instruments, he often uses a tuner. This is just a graph of a tuner. A tuner is a measuring device, but it doesn't measure pitch really. It gives the player only an indication of how to match the pitch. Concert A is defined as having 440 Hertz, meaning that the saxophone reed vibrates 440 times per second. So if I were to play the note A and the needle would be to the left where the minus sign is, the pitch would be too low. If it were to the right of 0, then the pitch would be too high. So there's two reasons why I took the saxophone as an example in this small lesson. Firstly, you can change the pitch of a saxophone, that's to say the frequency, by adjusting the mouthpiece. And if I would have to lower the pitch, I would move the mouthpiece away from the normal position, and it would have just a longer neck and would be increasing the distance, and I would thereby lower the frequency. It would really be like making the instrument a bit longer, and that changes the pitch and makes it lower. If I had to heighten the pitch, I would move the mouthpiece in the other direction. I would move it closer to the neck, and I would decrease the distance here, and thereby I would shorten the instrument and would increase the frequency. So saxophone tuning is quite a good example for the relation of instrument length and frequency. That's also the reason why a smaller saxophone like a soprano has a higher pitch than and a higher frequency than a bigger one. For example, a baritone is just because it vibrates faster. And this applies for the majority of all acoustic instruments. A larger instrument generally produces a lower tone than a bigger one. Think, for example, of a small violin, a bigger viola, and an even bigger cello or a big double bass. Secondly, I chose to speak about the saxophone because it only produces one note at a time. So if you hear a saxophone playing, how do you know it's not a trumpet or a flute or a guitar? The reason for that is embedded in the frequency character of any instrument, because pure sine waves, they don't exist, like the ones I symbolized here, they don't exist in nature. Instruments can't play them. So any sound has several frequencies. One of them is the fundamental, and added on top of the fundamental are several overtones, higher frequencies or partials, with different amplitudes, which sound simultaneously. So if I would play the note A on a saxophone, we would see in a spectrum analyzer a picture like this. We would have here the frequency 200 Hertz, there would be nothing at 200 Hertz, but here at 400 Hertz we would have big amplitude, and then there would be several overtones with varying amplitudes, and this combination of the partials makes up for the special sound of the saxophone, for the special sound of a trumpet, for a guitar, a flute, or anything. And even when playing the same note, if you play an A on a trumpet, it sounds different than an A on a guitar or on a saxophone. So to sum things up, slow vibration means long frequency, low pitch. Fast vibration means short frequency, high pitch. And remember, frequency is not connected to amplitude. I hope this little lesson has added to your understanding of the concept of frequency, and I thank you for watching this video.